Hello, organic chemistry students. This screencast is going to cover cycloalkanes up through 5 carbons, so cyclopentane. Cycloalkanes have the general formula CnH2n. Now, if we had propane, if we had a 3 carbon straight chain and we put 2 hydrogens on every carbon atom, that would be our CnH2n. And to make straight chain propane, we'd actually need that plus 2. If you'll recall, the formula for an alkane is CnH2n plus 2 when it does not have a ring. And so the reason we don't have this plus 2 on our cycloalkanes is because we've gotten rid of these 2 hydrogens on either end of the molecule to imagine the carbons becoming a ring. So they don't actually look like that, of course. Cyclopentane actually looks like a triangle, where every point, of course, represents a carbon atom. And each of these carbon atoms are going to have 2 hydrogen atoms connected to it. So there's your CnH2n. Well, N is just 3 in the case of cyclopropane. In the case of cyclopropane, these bond angles are 60 degrees. And so that's really small compared to the desired tetrahedral form of carbon single bonds would be 109.5 degrees. So that's greater than 90 degrees. That 60-degree angle of cyclopropane is really small. And so this has a lot of ring strain or angle strain, and that occurs when a bond angle is really compressed or expanded compared to what it ought to be. And so in this case, it ought to be 109.5 for a tetrahedral carbon. And so all that added potential energy due to tightening up that bond angle to an angle that's so much smaller than carbon's ideal bond angle is added as ring strain. So cyclopropane is really reactive. That ring strain makes it highly unstable, highly reactive molecule. If we were to go up to cyclobutane, just looks like a square, right? But it's got our 4 carbon atoms, and we know that square is going to have 90-degree bond angles. And so, that's improved over cyclopropane. It's not quite as reactive as cyclopropane, but it's still a far cry from the 109.5 that we're looking for that ideal bond angle. And so that's going to be reactive too. So cyclopropane, cyclobutane are really reactive, a lot of ring strain or angle strain. So the most common cycloalkanes that actually do occur in nature then are 5 and 6-membered rings. Nature loves 5 and 6-membered carbon rings, and we find tons and tons of those. And so if we go to that 5-membered ring, looks like a pentagon, and that planar cyclopentane, we're going to look at some structures of cyclopentane more in just a minute. But that planar cyclopentane has bond angles of 108. And so that 108-degree bond angle is vastly improved over cyclopropane and cyclobutane 60 and 90-degree bond angles respectively. So that 108 is much more stable. And so we'll look at that more in just a second. So let's stop for a minute and work a little bit on naming alkanes. So to name cycloalkanes, what do we need to know how to do? Well, we need to know our prefixes. We need to know the prefix for the name of the corresponding open chain. So for example, for 5 carbons here, we need to know that that's pent. So that will be pentane for all single bonds. And then we just need to put cyclo in front of that. So that just becomes cyclopentane. If there's only one substituent coming off of cyclopentane, we don't have to give it a number. So let's say that all we did was had a 1-carbon group coming off cyclopentane. Well, that's just methyl cyclopentane because you can start wherever you wanted to. So of course it's at the assumed 1 carbon, but you don't need to report that. You just call it methyl cyclopentane. If there's 2 substituents, we're going to number from the substituent that is lower alphabetically. So let's say that we have cyclopentane and we have a methyl group on it and an ethyl group on it. Well, methyl group starts with M, ethyl group starts with E. So we might as well put this as our 1 carbon because it's going to be first alphabetically. So we kind of have a choice of, which direction we're going to go. Might as well have the 2 be methyl and the 1 be ethyl. And so then you would have 1 ethyl, 2 methyl, pentane rather. We're on pentane now. Okay, if there's 3 or more substituents, you're going to number to give them the lowest overall set of numbers. And so if we want to think of an example of this, our methyl and our ethyl were handy. And maybe we'll throw a propyl group on there just to round things out. So we've got a methyl here, we've got an ethyl here, and we've got a propyl. And now we don't necessarily go by alphabetical order, we look at the numbering. So we pick a place to start, and it's always a spot where there is a group already. We know we want to start somewhere where there is a carbon group. We could start right here and go 1, 2, 3, 4. That way we'll have groups at 1 and 2 and 4. That takes advantage of some pretty low numbers. If we started down here with our 1, we'd be at 1, 2, 3, 4, and 5. So 1, 4, 5 is not going to be preferable. 1, 4, and 5 is higher than 1, 2, and 4. So we don't want 1, 4, 5. We could see, we know that this numbering convention is out. You can look for something else. You can look for, say, starting right here, 1, 2, because you're like, oh, I know I need a 1, 2, 3, 4, but then this one ends up being 5, so that just doesn't work out. So we need to stick with that 1, 2, 4 convention, and from there we alphabetize and we go, okay, put the F and then the meth and then the prop. So we're actually going to have 1 ethyl, 2 methyl, and 4 propyl. But note, these are ending up alphabetical by chance on this particular one. The numbers didn't necessarily have to come in order 1, 2, and 4. What we have to do is we have to alphabetize, and what we have to do is pick our lowest possible set of total numbers. So let's do some more naming examples. In this first one, and by the way, this would be a great place to pause and try some of these on your own. But let's name this as our parent chain. So we think about the shape of that. I like to just think about the shape. Oh, there's a pentagon, cyclopentane, where you can count that there's 5 carbons there. Cyclopentane, and then it's really easiest named with a common name for this. You've got 1, 2, 3 carbons, so propyl, but you're connected to the center of the 3 carbons, so isopropyl. Interesting note, iso does not have a dash between iso and propyl. Iso is actually one that you do alphabetize by. Over here, we've got cyclohexane for the root of our name. Oops, need that L. Not sure we're going to be able to read that. Okay, over here, we've got cyclohexane. Right here. And then we've got some groups on cyclohexane. A 1 carbon group is methyl. And over here, we've got a 1, 2, 3, 4 carbon group. 4 is butyl. Let's give it a common name of T-butyl. You need a dash between T or tert and butyl. And you actually alphabetize by the B then. You ignore the tert, the sec, or the N when you're alphabetizing. So then butyl actually comes before methyl. Since butyl is going to come first, let's give it the 1. So it's going to be a 1 and a 4 in either direction. So let's give butyl the 1 and methyl the 4. And then we end up with 1 dash T dash butyl dash 4 dash methyl. Running out of room a little bit. I don't have to have a space there. 1 T-butyl 4 methyl cyclohexane. Check out this guy. If it doesn't come to you right off the top of your head, 1, 2, 3, 4, 5, 6, 7, 8. 8 is an octagon, so octane. And then, of course, this is cyclo. So cyclooctane looks a little goofy with its double O's, but yes, it is cyclooctane. And then over here, well, we've got another cyclohexane. It's got a methyl group. And then 1, 2, 3, 4 carbons here. It's easiest to name these 4 carbons as a group with a common name for that butyl group. If we look at this carbon of interest that was connected here to the ring, it's connected to only one other carbon, but yet there's an isomer here, a branch off the second to last carbon on the chain means that it's actually iso. So this one would be isobutyl. Remember, iso is the one that doesn't get a dash and actually does do the alphabetizing by the iso. So we've got an iso and a methyl. So iso is going to come first. So we've got 1 dash iso with no dash, butyl, and 2 dash methyl cyclohexane. Here is our unstable cyclopropane. And we've got a methyl here and an ethyl. They're both on the same carbon. We do need to number this. You might think, oh, they're on carbon 1. You don't need to number that. But what if the methyl were on 1 and the ethyl were on 2? You know, one could be on carbon 1 and one could be on carbon 2, for example. What if methyl, what if ethyl? Let's draw ethyl, because otherwise the way I've drawn it looks goofy. Maybe this. Anyway, what if ethyl were here and methyl were here? Those would be on the 1 and the 2. So let's go ahead and say 1, 1, but ethyl is going to come before methyl. So we're going to have 1 ethyl, 1 methyl cyclopropane. So you know you've been in organic chemistry way too long when every time you see a stop sign you shout, cyclooctane! I mean, that might be the time to stop with the organic chemistry homework for a little bit and take a break when every stop sign looks like cyclooctane. Thought we needed a little comic relief at this point. So next up we have cyclopentane, and let's look at cyclopentane in a little more detail than we did before. So in planar cyclopentane, all of the CC bonds are the whole thing is going to be planar. So these guys are all bisected by the same plane, and their bond angles are all 108. So just imagine your perfect pentagon is going to have all bond angles of 108 degrees. And that differs only slightly from 109.5 for tetrahedral. So that sounds pretty good. Not so much angle strain. When we think angle strain, think cyclopropane. That strain, the strain from having tiny angles, or too big of bond angles too. But here's a problem with that cyclopropane. All of these hydrogens are lined up eclipsed. And we know that having things eclipsed like this is not favorable. Right? And so since these hydrogens are all eclipsing, That is not so great. That creates torsional strain. That's the idea that, remember, butane tries to twist to relieve eclipsed conformations. It twists, or I think of it as contortion, right? It's twisting to fix this. It's going to want to twist a little bit to fix all of this eclipsing, because this eclipsing of all these hydrogens is just too much. So ring strain was better because we've relieved the bond angle, to 108, but we've picked up some torsional or eclipsing strain along the way. So what to do about that? What pentane does, we don't do anything, right? But what cyclopentane does is what's called a puckered or envelope conformation. So it moves into this puckered or envelope conformation, where we like to think of it as the point. So if I've got my pentagon, or let's say my envelope, think of this as the part of the envelope you're going to stick your letter in. So here's the bottom part of the envelope, here's the flap. And what we're doing is, here's the envelope, laid out with the flap open. We're just putting the flap up in midair a little bit. So we're just lifting the flap on the envelope a tiny bit and puckering it up into the envelope conformation. And what it does is it twists it enough. It's that torsion or that twisting enough to get some of these hydrogens to not be as eclipsed as they were. You're relieving some of that eclipsing strain, some of that torsional strain. And when you relieve some of that torsional strain, guess what you replace it with? Some angle strain. So when we pucker into the envelope conformation, and again, when cyclopentane does this, it, you know what? Now its bond angles are worse. Now its bond angles are 105. We brought them in a little bit. So you're kind of fixing one thing and causing another problem. But cyclopentane is going to spend more time in this puckered envelope conformation. So it's overall a lower energy conformation for cyclopentane. Next, we're going to talk about cis-trans isomers of cyclopentane. So isomers always have the same molecular formula. The cis-trans isomers have the same connectivity of the atoms. So for cyclopentane, when we're looking at the two different cyclopentanes here, they both have the same connectivity, where they have these 5 carbons connected in a ring. They have the same number of hydrogens on each carbon, but they're just a different arrangement of those atoms in space. But to backtrack again, they do have the same molecular formula. There's 5 carbons in the ring, and then there's 2 more carbons here. So we see there's 7 carbons. If we look at hydrogens, I could count 3. 3 is 6. And I could count them 7, 8, 9, 10, 11, 12, 13, 14. C7, H14. And if I wanted to verify over here, I'd go, okay, 5 in the ring, 5 carbons in the ring. Here's the 6th and the 7th carbon. And then for my H's, I have 3 and 6 right here. 7, 8, 9, 10, 11, 12, 14. So of course I have C7, H14. So same molecular formula for these two drawings. Same connectivity, 5 are connected in the ring. There's 1 carbon coming off of the first carbon in the ring and 1 coming off the second carbon. So these 2 carbons that are coming off the ring are both just, 1 carbon bond in between them, separating them. So that's the same connectivity. So then they differ in their arrangement in space. So on the left, these 2 methyl groups are on the same side. On the right, 1 methyl group is down and 1 methyl group is up. So on the left, when they're both on the same side, that's called cis. Cis for on the same side, trans for the methyl groups being on opposite sides, 1 up and 1 down. They can't be interconverted. It's not like staggered and eclipse where we can just twist around a single bond and interconvert these. That ring really fixes the structures so that cis is different than trans and it can't be interconverted. And so it's often looked at like looking upon this edge and seeing the two methyl groups down. Or you can represent two down with wedges. And you could represent one up and one down, one up with a wedge here and the other one back with a dash. So cis can be represented by, two dashes. We've got dashes right here, or by two wedges. I mean, and another way to draw this, and it doesn't matter which way you do it, but you could also just draw this with two wedges. That will mean cis also. You actually don't have to write the CH3 either. You can just leave the wedge, and the viewer assumes that this is a carbon on each wedge. So you'd assume that each wedge is a CH3. And then, so two different ways of drawing this again that you can view from an edge. And the idea when you're viewing from an edge is that almost like these are wedges coming out at you. So almost like these two carbons are coming out at you and you're viewing it a little bit on edge. So almost like this whole thing is wedged out at you. And then when you're holding that directly in front of you, you're going to be able to see a group up and a group down. And if those methyl groups are on the same side, for example, we call that cis. So the lines are always straight up and down here. That's really important. If they come off at weird angles, it's really hard to tell if it was supposed to be cis or trans. The only way they get to come out at angles is if you just go ahead and you wedge and you dash them, because then we're going to be certain if you meant cis or trans. So lines straight up and down, or wedges and dashes. Those are really your good choices when you are asked to draw cyclopentane.